Hi everyone, I'm Anurag Gorkar and today I'll be discussing the dominating set problem, a classical NP-complete problem in graph theory. This ties into the broader topic of computational complexity, reductions, and problem classes. Here is a quick overview of the topics I'll cover. We'll start with the decision versus optimization problems, then explore complexity classes, then dive into the dominating set problem, its definition, proof of NP membership, a reduction from vertex cover, and then conclude this presentation. We often distinguish between decision problems, which have a yes or no answer. For example, is there a path of length less than equal to k between nodes S and T, and optimization problems, where we seek the best solution, like the actual shortest path. Dominating set problem is typically posed as a decision problem in complexity theory. Let's quickly review all these complexity classes. Class P, that is, class P problems can be solved in polynomial time. Think of sorting or finding shortest paths. NP includes problems where a solution can be verified quickly, even if finding one is hard. Then we have NP hard problems, the hardest problems in NP, and NP complete, which are both in NP and NP hard. Dominating set falls into this NP complete category, which we will see shortly. Now we'll look at what the dominating set problem is. Given a graph G of vertices V and E and an integer k, is there a subset D of vertices with size less than equal to k such that every vertex is either in D or adjacent to a vertex in D? Think of it like picking a small subset of influencers in a social network that can reach everyone. Here is a visual set. Here, set 0, 3 dominates all the vertices in the graph, either directly or via its neighbors. This helps us to understand the intuition behind this problem. To prove that the dominating set problem is in NP, we consider a certificate, the set D of vertices. To verify it, we check two things. Its size is at the most k, and every vertex is either in D or has a neighbor in D. This can be done in polynomial time, specifically big O of V square. So it is in NP. Now we'll look at the reduction from vertex cover problems. To show that the dominating set problem is NP-complete, we reduce a known NP-complete problem, that is vertex cover, to dominating set. Vertex cover asks if there is a set of k vertices such that every edge is incident to at least one of them. We construct a complementary graph G dash where edges not in the original becomes edges in G dash, and we add self loops to every vertex. The dominating set problem on G dash then becomes equivalent to vertex cover problem on G. The key idea is that the cover in G ensures all non-cover vertices in G dash are adjacent to a vertex in the set. Because of the self loops, vertices in the set dominate themselves. This completes the logical reduction in both directions. Now we'll look at the polynomial time transformation. The transformation of G to G dash, that is adding self loops and computing the complement, can be done in polynomial time. So the reduction is efficient, satisfying the requirements to show that the dominating set problem is an NP-complete problem. Conclusion. In conclusion, unless P equals NP, we can't solve the dominating set problem in polynomial time. Exact solutions are said to be exponential. In real-world scenarios, we often use heuristics, approximations, or fixed parameter algorithms to handle this challenge. Thank you for listening to this presentation.